Welcome to Norton Chemistry. Today we're going to be doing a revision video on bonding and structure. We've got some exam questions to go through at the end. Ionic bonding. An ionic bond is when there is electrostatic attraction between oppositely charged ions. And in a giant ionic lattice, each ion is surrounded by oppositely charged ions. So we use dot and cross diagrams to represent ionic bonding. So for example, in sodium chloride, we have sodium ions, which have a positive charge, and chloride ions, which have a negative charge because they've taken on an extra electron from the sodium. And the strength of ionic bonds depends on the ionic charge. So the greater the ionic charge, the greater the electrostatic force of attraction, so stronger ionic bonds. And then ionic size. So for example, smaller ions are closer together in the lattice, so they have stronger ionic bonds. And then the properties of ionic structures, so these are a result of ionic bonds. High melting/boiling points, they're soluble in polar solvents, and they conduct electricity when aqueous/molten, but not when solid. I've got a question asking us to explain the properties of ionic structures. The high melting/boiling point is due to the strong ionic bonds, which require a lot of energy to overcome. And they're soluble in polar solvents because the ions can be surrounded by the polar solvent, for example, water molecules. And because the ions are charged, they can interact with the polar molecules, and the ions can become pulled apart by the polar solvent, so they enter an aqueous solution. So in water, the positive ions are attracted to the delta negative oxygen atoms, and the negative ions are attracted to the delta positive hydrogen atoms. Then they conduct electricity when aqueous/molten, but not when solid, because when ionic lattices are solid, they're held in the lattice structure by the strong ionic bonds. So the ions aren't mobile, they're not free to move, they can't conduct electricity. Whereas when they're aqueous or molten, the ions become mobile as the ionic bonds are overcome, so they can conduct electricity. Then covalent bonding. So the definition of a covalent bond is a strong electrostatic attraction between a shared pair of electrons and the nuclei of the bonding atoms. So for example, we've got water, which has covalent bonds between the oxygen and hydrogen atoms. So it has two single covalent bonds, and then it has two lone pairs of electrons, and then oxygen has a double bond, and each oxygen atom has two lone pairs. And then we have something called the dative bond, which is when one of the bonding atoms donates both shared electrons in a covalent bond. So for example, in the NH4+ ion, one of the bonds is a dative covalent bond because the nitrogen atom is the only atom which donates the electrons in the bond. And then average bond enthalpy is defined as a measure of the enthalpy required to break 1 mole of a covalent bond. So then we have simple molecular structures. So for example, chlorine, water, ammonia, and they have low boiling points. So in the solid state, they're held together by only weak intermolecular forces, which require little energy to overcome. So electron pairs repel each other. So arrange as far apart as possible in space. Lone pairs of electrons repel more strongly than bonded pairs. So we can see in water we've got lone pairs which are on the oxygen atom, and they're not in any bonds. And then we have the bonded pairs between the oxygen and hydrogen atoms. And we have a molecule of CH4, methane. When we draw a single line, that just means we're in the plane of the paper. Then when we have a dashed line, that means we're going back into the paper. And then when we have a triangle, that means we have an atom coming out of the plane of the paper. Don't worry about this too much, you just need to remember how to draw the molecules for specific shapes. And molecular shape is determined by electron pair repulsion theory. So we've got a table, and we're going to fill this in. So if you've already learnt this in class, try and have a go and fill it in, but I will go through it as well. So we have lots of different shapes of molecules, and you need to memorize these shapes and the number of electron pairs that contribute to it, as well as the bond angle. And also it's good to know examples for each. So we have a linear shaped molecule, and this is where we have 2 bonding pairs and 0 lone pairs, and the bond angle is 180 degrees. So an example of a linear molecule is carbon dioxide, CO2, because we have 2 bonding regions, these double bonds. So we refer to double bonds as a bonding region. So it's not 4 bonding pairs, it's just 2 bonding pairs. And then we have no lone pairs on the central carbon atom. So these electron pairs, they're going to arrange as far apart in space as possible, which is 180 degrees apart, remembering that the angle of a straight line is 180 degrees. Then we have trigonal planar, And this is where we have 3 bonding pairs and 0 lone pairs. So the bond angle is 120 degrees. An example of a trigonal planar molecule is boron trichloride, which we represent like this. So because all of the chlorine atoms are in the same plane, we just draw a single line for each. And then a tetrahedral molecule has 4 bonding pairs and 0 lone pairs. So the bond angle for this is 109.5 degrees. And an example is, as we saw earlier, CH4. And we have 2 atoms in the plane of the paper. And then we have 1 atom going into the plane of the paper and another atom going out of the plane of the paper. And as you can see, we kind of get this pyramid shape when we draw lines between the outer atoms. And then trigonal bipyramidal is when we have 5 bonding pairs and 0 lone pairs. And the bond angle is 90 degrees and 120 degrees. So an example of a trigonal bipyramidal molecule is PCl5. So we have 3 atoms in the plane of the paper, and the bond angle here is the 90-degree bond angle. And then we have 1 atom going into the plane of the paper, and we have 1 atom coming out of the plane of the paper. And the bond angle there is 120 degrees. Then octahedral is where we have 6 bonding pairs and 0 lone pairs, and the bond angle is 90 degrees. So an example is SF6, and we represent it like this. And the drawing of octahedral molecules is probably the most important to remember, because it comes up in module 5 in transition elements. So we have 2 atoms in the plane of the paper, 2 atoms out of the plane of the paper, and 2 atoms into the plane of the paper. So it's relatively easy to remember. Then we have non-linear molecules. So this is where we have lone pairs involved. And in a non-linear molecule, we have 2 lone pairs and 2 bonding pairs. And the lone pairs reduce the bond angle because they repel more strongly than bonding pairs. So the bond angle in a non-linear molecule is 104.5 degrees. And an example of a non-linear molecule is H2O, water. Then finally, we have pyramidal molecules. And this is where we have 3 bonding pairs and 1 lone pair. And this reduces the bond angle from trigonal planar, which is 120 degrees, to 107 degrees. So an example of a pyramidal molecule is ammonia, because the nitrogen has 1 lone pair and 3 bonding pairs. Okay, so bond polarity. So the definition of electronegativity is the power of an atom to attract the pair of electrons in a covalent bond, and it's affected by the nuclear charge, the atomic radius, and the shielding by electrons in inner shells. So nuclear charge is dependent on the number of protons in the nucleus. Atomic radius is dependent on the number of electron shells in the atom. And shielding by electrons in the inner shells is also dependent on the number of electron shells. So this means that electronegativities increase across periods and decrease down groups, making fluorine the most electronegative atom. So in the Pauling scale, a method developed by Linus Pauling of comparing the electronegativities of different atoms. Most electronegative atoms are those that are furthest to the right and the highest up in the periodic table. So if you look at the periodic table, fluorine is far to the right and is also at the top of the periodic table. You also have oxygen and nitrogen, which are the second most electronegative atoms. And in the Pauling scale, the higher the electronegativity value, the higher the electronegativity of the atom. Polar bonds form between atoms with different electronegativity values. So fluorine is more electronegative than oxygen because it has a greater nuclear charge, as it has an extra proton in its nucleus. It has a smaller atomic radius, as the greater nuclear charge means that the outer shell is pulled closer to the nucleus. It has the same shielding as oxygen, so the nucleus has a greater attraction to the electrons in the covalent bond. So polar bonds form between atoms with different electronegativity values, causing a permanent dipole. Partial negative charges and partial positive charges show that a bond is polar. Molecules containing polar bonds are not always polar. The symmetry of polar bonds can cancel the effect of any permanent dipole. So, for example, CCl4 on the left is not polar, as the molecule is symmetrical, and the dipoles oppose each other, causing them to be cancelled out. On the other hand, CH3Cl is a polar molecule, as the dipole is not opposed and is not cancelled out. So this CCl dipole, because carbon and hydrogen are very similar electronegativities, there's no dipoles on these bonds. So there's only one dipole, and so the dipole isn't cancelled out. Intermolecular forces. So induced dipole-dipole London forces are caused by the temporary unequal distribution of charge due to the constantly moving electrons in molecules. So in molecules, electrons are always moving, they never stop moving. And the temporary dipole can induce a temporary dipole in a neighbouring molecule, and the two dipoles will be attracted to each other. These forces occur between all molecules, and it's the weakest intermolecular force, meaning it requires little energy to overcome. Then we have permanent dipole-dipole forces, which are caused by molecules with a permanent dipole being attracted to the opposite charge in other permanent dipoles. They're stronger than London forces, but they're weaker than hydrogen bonding, which is a strong dipole-dipole attraction between the lone pair of electrons on a highly electronegative oxygen, nitrogen, or fluorine, partially negative atom of a molecule, and a delta positive hydrogen atom on a neighbouring molecule. Hydrogen bonding is responsible for some of the anomalous properties of water. So, for example, it allows ice to be less dense than water, as hydrogen bonds hold the water molecules apart at a fixed position, forming an open lattice. So this is why when water freezes, it expands. Also, water has a higher melting and boiling point than expected due to hydrogen bonds being the strongest intermolecular forces. So most simple molecules only have London forces, which require little energy to overcome, whereas hydrogen bonds require a lot more energy to overcome. So water has higher boiling points than most simple molecular structures. So you can see a diagram of a hydrogen bond. They always ask you to label the hydrogen bond when you're drawing a diagram of it. And you can see it's between the delta positive hydrogen atom on one molecule and the lone pair of electrons on the highly electronegative delta negative oxygen atom on the other molecule. So we've got some exam questions to go through. Phosgene, COCl2, exists as simple molecules. The displayed formula of a phosgene molecule is shown below. Draw a dot and cross diagram of a phosgene molecule. Show outer electrons. So we can see that we have two single bonds between the carbon and chlorine atoms and one double bond. So we need to account for that when we're drawing our dot and cross diagram. So we have a double bond between the carbon and oxygen atoms, and then a single bond between the carbon and chlorine atoms. And then the chlorine atoms are going to have 6 electrons each as lone pairs. And then the oxygen atom is going to have 4 electrons as lone pairs. Name the shape of a phosgene molecule and explain why it has this shape. So we can see that the carbon atom, which is the central atom in the molecule, so all the other atoms are bonded to the carbon atom, has 3 bonding regions. So we count this double bond as just one bonding region. So that's a trigonal planar shape, so it has no lone pairs and 3 bonding pairs. So the whole reason for the shape of molecules is electron pair repulsion theory. Thanks for watching. Be sure to check out my website to purchase A-Level Chemistry revision resources. Make sure to check out my other videos, including my electron structure topic revision video. It should be in the top right hand corner now.